This is the second video on an introduction to a first course in modelling, analysis and control, and now we're going to focus on open loop control. Some background then. The first video introduced the concept of systems behaviours and performance, and we need a language and tools to define, measure and classify these behaviours, which will therefore enable us to do systematic design to improve performance. Next, we want to consider how we control behaviour. So having decided what behaviour means, what behaviour would we like, the next question is, how do we achieve this? How do we ensure a racing car is the fastest on the track or goes at the ideal speed? How do we fill a cup to the brim but not overflow? How do we cook something perfectly? Some examples then. There are numerous examples of simple processes where we wish to control the output of a process to a given value. So humidity and temperature for air conditioning to make the room comfortable. Altitude and attitude of a cruising aircraft, especially a passenger one. The spin speed in a DVD drive, otherwise it will not work correctly. Mixture ratios of fuel and air in an engine to make sure you get optimum power, but also to manage pollution. Pressure of a fluid entering a turbine, and so forth. Now all these cases and many others which I'm sure you can think of, it's important for the output to track the target. So here's an example. Open loop control. Imagine you need to get your car to 60 miles an hour, but, and here's a big but, you are not allowed to look at the speedometer or to hear the engine revs. How would you do it? Now, in all likelihood, you would call on experience and memory, and you would have to estimate the foot pedal or the throttle position I've called it U, required to reach the desired speed. So how would you do this estimate? You might estimate the steady state gain of the car. Here I've called that G of 0. And then you would say, well, the input I need is going to be 1 over G of 0 times 60, 60 being the desired speed. Now, will this work? So let's consider a realistic situation. You think that G of 0 is 15. So therefore, you're going to say, I need a U of 4 to get me to 60 miles an hour. However, what if G of 0 was actually 20? Then in reality, you would only need U equals 3, but you've decided to use U equals 4. So let's see what happens. You expect the speed to follow this brownish curve and get to 60 miles an hour. But in fact, you're going to end up at 80 miles an hour because your estimate of the gain was wrong. So you've got a big error in speed, you're going to get a speeding ticket. So remember, you're not allowed to see the speedometer. You don't actually know what speed you're doing. So the key thing is your estimation or your guessing was flawed and you end up with a problem. Some other examples, preparing a boiled egg and toast. So the instructions say the egg should be boiled for 180 seconds, but you do not have access to a watch. So you're going to guess, was it the right time? Well, in all likelihood, your egg will not be well cooked. It will be either undercooked or overcooked. You have a grill to make toast, but you're deaf and blind. So you set a timer to toast the bread for exactly 120 seconds. Are you going to get good toast at the end? Well, probably not, because 120 seconds might not be the right time. A manufacturing process. In order for a given process to work correctly, the temperature of an outlet flow must be exactly 41 degrees. So you mix hot water, coming at approximately 100 degrees, with cold water, which is at the outside temperature. And you do this by opening and shutting a tap to change the flow of cold water. But here's the critical point. You have no means of measuring the actual temperature of the mixed stream. So are you likely to get your 41 degrees? Well, obviously not. You're most likely to end up far too hot or far too cold because you've made a guess and you've got no way of measuring whether it's worked or not. Some other examples then. So this heat exchanger is a bit like the previous example. So what we're going to do is guess the required steam flow to achieve 30 degrees in a combined flow. And then we're going to look at what happens when you have some disturbances affecting the system. Now here's the key thing. You've got to pretend you cannot actually see what is happening. So you've got no information to update your guess. So Let's find this heat exchanger. Here it is. So here's the heat exchanger. So if I start this running, now you'll see I'm going to just guess the steam flow. I'm going to put it here at 13. So I've just guessed. And now we're going to see, remember, in reality, you can't see if you're doing open loop. Have we got to 30 degrees? Well, you can see the steam flow over here has got to 40. Okay, so we made a guess, and our guess was wrong. So we get the wrong temperature. Now, what happens if we get some disturbances? So what's likely to happen is from time to time, the inlet temperature may change. You have no knowledge of this, so look, the inlet temperature's changed. What's that done? You can see our guess for the correct steam flow is now even further out. I've now gone close to 50 degrees, and this change in the inlet temperature I don't know about. And because I can measure nothing, I end up with even worse behaviour. Now I can also get changes like the fluid flow rate, I might not know anything about. Now here, increasing the fluid flow rate has helped us. But the key thing is, we're not getting to 30. This open loop is not working. Okay, next example, tank level. So we want to guess the required inlet flow to achieve 1 metre depth. And again, we're going to ask ourselves what happens when disturbances happen. So, and again, pretend you cannot actually see what's happening. So you've got no information to update your guess. So if we can find the tank, here it is. So we're going to make a guess. Let's guess the fluid flow should be somewhere about here. So you can see I've just made a guess, so I've got no clue if that'll work. Now I'm going to press continue. So are we going to get to the right depth? So you can see the tank's filling up, it's filling up, it's filling up, but it seems to be slowing down. Now, in reality, we can't actually see what's happening, but what you can observe is our guess is wrong. And because we've got no observation, because we can't actually see this, we don't know it's wrong, so we've got no way of correcting it. And again, we can make some errors. So what errors can we do? We can introduce an inlet disturbance flow. Okay, so what happens then is that every now and then there's a disturbance to the inlet. That doesn't seem to be working. Oh, there it is. So you can see this red jump shows you that the flow rate coming in is not what you think it is. And therefore, your actual depth is going to keep changing. So every time you get a change in this inlet flow, which you don't know about, the depth keeps changing. But again, in reality, you can't see this. You can't see this happening. And therefore, it's happening without you noticing, and everything is going wrong. Okay, so what's the weaknesses of open loop control? Why can't we control car speed with our eyes shut? Why can't we control the temperature of a mixed flow without a temperature sensor? Why is unmonitored cooking likely to fail? All of these systems lack a measurement or observation. That is a mechanism for checking what the system is actually doing. And without observation, we do not know whether the behaviour is correct, and hence we've got no information with which to update our system input. So, open loop control means no measurement of the output, and thus the input is an estimate. In practice, the estimate will be wrong, and hence the output behaviour will not match the target. Now, incorrect estimates can occur for many reasons. We can have incorrect estimates of gain, which is often denoted parameter uncertainty. We can have poor awareness of varying external conditions, such as wind, temperature, and so on, and these are often denoted as disturbances. Conclusions. For many systems, it's important to control the output to a specified value and with specified behaviour, irrespective of uncertainty in the model parameters and external disturbances, and open-loop methods will often fail. Now, humans use a concept called measurement feedback loop to achieve this, and we'll cover that in the next video. And this module then will introduce the mathematical and analysis tools that students need to introduce feedback in a systematic fashion and thus to automate the process.